and CCR.
Yeah, I got it.
John Fogerty was the lead singer for CCR, but
Clearwater.
then he left.
Oh.
Reliable.
Yeah.
What's the
What
fifth
was the
Star
original
Wars
place, Mr. Ron?
episode? Is it Empire? No.
It's Empire Strikes Back, I think.
It
Yeah.
is?
Yeah.
That's what I thought. Okay.
Yeah, Empire Strikes Back. Return of the Jedi.
It's Star Wars.
Yeah.
The new
Portion.
Fortunate Son, great song.
Yeah.
Which song?
Fortunate Son.
Wars.
Oh,
Oh,
Third episode, but like sixth movie made.
I think it's like four.
That was
I
most
don't-
recent movie.
So like I know how to select.
No, that was.
I don't know how to find which
Revenge of
one.
the Sith. Yeah.
Yeah, that's right.
Do you want to? Did we Google it?
The new ones.
I still don't understand how to use this. Just go on Google and be like how to select specific.
The system.
Okay. Here, this is
Syphilis.
okay. 421 through 560.
Did I ask you guys any of my geography trivia questions?
No.
I have these.
Oh,
I have
yeah.
some great geography trivia questions.
Oh, I made some middle school geography bead.
Here's like one of my favorite ones that's actually kind of math related. So I feel like maybe we discussed it.
Is this?
If you dig a hole, if you went from right here, Nashville, Tennessee, or
Australia.
Fort Wayne, Indiana, I forget where in Indiana you guys are.
Yeah, you got it. Fort Wayne.
Fort Wayne? Okay. Nashville, Tennessee, Fort Wayne, Indiana, not that far apart, okay? If you were to dig a tunnel through the center of the earth, out the other side, where would you be? Where on earth would you be? Definitely the southern hemisphere, because we are in the northern hemisphere. So it would be the opposite part. Or like
Probably in the Pacific.
Equivalent question,
Somewhere
like
in the Pacific.
Suppose that this was the North Pole. Suppose that right here is the North Pole. Where would the South Pole be? Equivalent question. If I was sitting at the North Pole, like if I reoriented my view of the world, this was the North Pole, what would the South Pole be?
Right. How specific of a place are you asking for?
Yeah, not that
It's
specific.
in the middle of the ocean. Right
In
under
other
the
words,
key
you
on
would
the
either
map.
tell me what is the body of water or what is the country.
South America.
Would
Would we be in South Africa?
Bengal, the
Bengal is like a region.
It's like under the.
Dig a
Indian
hole
Ocean.
straight from Fort Wayne through the center of the earth. Where would we be?
It's like the southern part.
Yeah, that's true.
What's the
So,
question?
yeah. So you saw.
In the middle of the Indian Ocean somewhere? Or the Pacific Ocean?
I said Indian Pacific. Do you know the answer? Are you?
Yeah,
Is this
yeah,
a game?
Southern Indian Ocean. Let's look at a map.
Does
This is
Ultimate
kind of
have a referee?
No.
No.
Sounds You're like the only you and Jesse. You and Jesse are the only people I lose to ever. But actually, I've been Jesse.
Stop!
I'm not gonna stop.
I'm literally going to murder
Okay.
you. And your family.
Yeah, we were looking at nowhere differentiable functions in calculus class today.
Nowhere.
Nowhere.
Nowhere differentiable. Continuous everywhere, differentiable nowhere. At no point does it have a standard line. Which, by the way, that wasn't, as I explained to my calculus class today, was an open question for centuries. If you have a function that is continuous everywhere, must there be some subset of points at which you can draw the tangent line? The answer is no, which is a very interesting result. You can have a curve that is defined everywhere, continuous everywhere, and differentiable nowhere. You cannot draw a tangent line anywhere. And it kind of has this fractal structure. You see, like if you zoom in on a point, you get the same structure in the picture that you have for the large scale structure. So it is self-similar.
So is that not considered a fractal?
No, it is a fractal. Well,
Why does it say like fractals?
well, because like this function is defined everywhere, so its large scale picture like continues forever, but this picture doesn't really continue forever. So it's not quite self-similar, but it has a local self-similar. Okay, so then we want map of the world. And then I want with coordinates. So here's, I feel like this might be interesting.
Oh, there we go.
So we are somewhere in this area here, or Sarah would be like up here. Okay, Sarah's farther north than we are. We're kind of around here, south of Michigan, by varying amounts. And so looks like our longitude, we're 80-ish degrees west of the prime meridian. Latitude, we're about 40 degrees north. So the antipodal point, in other words, the exact antipodal, opposite pole, okay, would be at, I need to be 180 degrees different with respect to longitude. So 80 degrees west needs to become 100 degrees east, and then 40 degrees north needs to become 40 degrees south. So it's somewhere here, South Indian
So
Ocean.
pretty south.
That's very south.
Yeah, you see, like Tasmania is like the corresponding, or New Zealand. Tasmania and New Zealand is kind of like roughly where you would be.
Just really hard to get
Yeah, yeah. So don't actually do it.
Okay.
Plus, when you actually went through the center of the Earth, bad things would happen.
You would stay there.
Yeah, you just.
You wouldn't. I don't even think you'd make it through like the mantle.
Oh yeah, but if you.
Yeah. Plus, yeah, that's also true. The physical aspect of the digging will be different.
Yeah.
Do you know, like, if you were,
Yeah,
if you
get
could
stuck
fall
in the middle.
through it, how long it would take you to any chord through the Earth sphere? Like, how long it would take you?
Well, so now,
You
what
would
is
never
the,
get
what
to
is
the other
what is the
side.
radius
Yeah,
of
you
the
would
Earth?
never get to the other
Yeah.
side.
You should go in the middle.
No, I know
that's
through, and you
no,
get to a
it's
certain
far
point, and the
from
gravity of the center would pull you
Ah,
back,
very
and then you just
Well, but see,
get
okay, so
stuck in the
now
middle.
this is where kind of your view of Newtonian physics needs to adjust a little bit, because whenever you do Newtonian physics, you treat any large mass as a point mass, but really you shouldn't do that. It's not actually true that all of the mass of the Earth is concentrated at the center. That's not actually true. The mass is distributed over the Earth. So like, as I'm standing on the surface of the Earth, I'm kind of on top of the world, actually, as I see it. And so the whole mass of the Earth is below me. But if I'm like under the Earth, now the mass of the Earth is kind of around me. So gravity is kind of like pulling me in all these different directions, actually.
True, but you get to the point where you're so far, you're going out the other side,
The rest
you're
of
so
the-
far that the stuff below you is now supposed to pull you back in.
Yeah.
So I think that at some point your acceleration would become zero, but I don't think that your velocity would then become zero.
That means that you were traveling at.
I think you would actually kind of like, you would be like a spring that you pulled and let go. Like you would fall through and you would fall most of the way to the other side, but then like gravity would start to pull you back.
Yeah.
And you would kind of start to oscillate
what I-
like this.
yeah.
I think that's an interesting question. Yeah, I never thought of it.
But
Like suppose that the Earth was hollow, was hollow after like 1,000 feet of depth. Then what would happen? Then I guess you would kind of fall through and then come back up. That's interesting.
If it was hollow after 1,000 feet of depth, there might not even be enough Earth.
Yeah, I don't know. The mass would be very different, of course. The mass would be very different. I don't know. I also don't know things like
Might not be spherical.
what is the density of the center of the
Not
Earth?
that many of us.
What is the density of the things near the surface of the Earth? Those are interesting questions. I don't know.
It's gotta be more
what
dense
Dad
than
says as a physicist is when traveling through a chord, any chord, even the diameter of the Earth. Now he hasn't specified how he travels, so I don't actually know a lot, but it takes 90 minutes, no matter what chord.
To go like through the center of the Earth?
Not just that he hasn't
Have it
specified. I
rotating?
forget how he said he traveled. I don't know if he
I
like
see.
jump through a whole thing. He said it takes 90 minutes.
Interesting.
Oh, no matter where you are.
I could call my dad to clarify.
Not necessarily. Maybe another time.
Not yeah, not now.
Yeah.
What now?
Eggs. Yeah.
Around the.
You mean specifically on
What's that?
Dyson spheres.
Oh.
Dyson spheres?
Yeah.
What are those?
Oh, it's kind of Dyson.
Is it the inventor Dyson?
I think so. He had
He
this.
makes the vacuum?
Oh no,
No?
it was some other guy.
Probably
some other
older.
guy named Dyson, and it was like he had this theory that you could theoretically build a giant sphere around the sun and then live on the inside of the sphere.
Why? I don't get it.
I don't know, like just
Like, no, what? But isn't it like super hot inside this?
Yeah.
no, not if it's not if it's big enough.
That'd be
It's just like when like Plato and early philosophers
It was
believed
just
like
like it was just like a
the
practice.
orbits were like
world
egg
building.
shaped, like spheres,
Oh,
that kind
that
of
was
idea. Or Ptolemy, sorry.
Ptolemy. I got you.
Yeah,
Yeah,
that's.
it's In history of science, probably you guys did some of it. Did you ever do? Anybody take history of science? Oh, well, you all should because it's awesome. You learn about like, did you do like epicycles and the history of orbits and stuff? Okay, so you also learn about that.
In Western and we talk about the history of the cosmology and how it came to be like that.
All right, official good morning to everyone.
Official hello.
Nice talking. Nice talking about fun random stuff. Okay. Here's what I want to do today. We have a little bit of homework about the intermediate value theorem, some cool results related to the intermediate value theorem, and then we are going to start to move toward this result that we mentioned about the soccer ball at the end of last week. Okay, so I think we had 2 exercises, or were there 3? There were 3. Let me just remind myself. Here's homework from Walter. Oh, we had compute the Euler characteristic of a cube, right? Was that the last one?
Yeah.
Okay.
I think it was.
Or was it not?
Teacher.
Oh, that's right. Okay. Good. Okay, so we have 3 exercises. Anybody want to do number 1? Let's see if we can get these worked out. Anybody want to volunteer to do number 1?
Forgot about that.
Here, he's one of you, number 1.
What?
Would anyone like to do number 1?
Ankur would.
Sure, I can do 1. Yeah.
All right, good man. Appreciate that, Ankur. How about number 2? Yeah, we can't all just volunteer Ankur for
I can do it.
Sarah can do it. Good. Sarah, I did receive your homework this time.
Oh, really? Great.
The share document thing is working, so that's good. Sarah now shares her homework with me as a Google document. It's a good plan.
Shara.
Well done, Jacob.
You are kicked
Alright,
out.
then we have number 3. Anybody want to do number 3? And Aaron, good. Okay. That's 3 people. So now we're going Ankur for number 1. Okay, Ankur, we are looking at your solution for number 1. Take it away.
Alright, so it was saying that if you have 2 functions, f of x and g of x, and f of a starts out lower than g of a, and f of b starts out or ends up greater than g of b, and it's like closed on this interval, do they intersect? Or like prove that they have to intersect? And so because of the mean value theorem, you know that f of x...
Intermediate value theorem.
Intermediate value theorem, f of x must cross every intermediate value between f of a and f of b, and that's the same for g of a or g of x. And since the values like intersect, as in like it goes from a to b and the other one goes from b to a, so the values cross over at some point, then therefore the functions must cross over as well, and there has to be a point which they cross over, which is f of x equals g of x.
Okay. I think your intuition is good, but I think the wording we could tighten up a little bit. Do you have a board in your room?
A board? It's connected to a wall.
No, that's okay. Is there any way that you could kind of draw a picture of what you're saying and kind of sync it up?
Yeah.
It's that.
That would be awesome. We can see your board perfectly.
No, it's important.
Yeah.
Hopefully it was just review stuff.
So I'll make f of x black and g of x blue.
Okay.
Can you hear us? I don't know.
Yeah, I can hear you.
So this is so what I'm saying is that You know that one starts out below the other and ends up on top because of the statement. Because of the statement that f of a is less than g of a, which is true here, and f of b is greater than g of b, which is true here. And because of the intermediate value theorem, it has to cross all the values between. Well, there's also like an interval here. It has to cross all the values between this interval and this interval. And since f of x crosses the values this way, and g of x crosses the values this way, the values intersect at some point, and so you know that the lines have to intersect at some point.
Yeah, your intuition is perfect. Your intuition is perfect. One thing I would caution you about is just, there's one statement that you make that I don't agree with, which is this. It is possible that the function f looks like this, and the function g looks like this. Okay. So in particular, it's possible you make this statement that one of the function has to slope up and the other has to slope down, but that's not true. Okay. It's possible that both the functions are always increasing. Okay. But what we do see in both cases is that the functions are intersecting at some point. So the intuition is there. The intuition is there. Yeah, what he's saying is basically this. Yeah, and it does require a little bit of extra justification. So I think I'm going to see if we can get a little more out of this. But the function f has this range, and the function g has this range. And so he's arguing that there has to be some point where the function g crosses into the range of the function f. And so it's going to have to, since the function f is always within this range, it's going to have to hit it somewhere. Which is true, but we can make the argument more rigorous. We can make the argument much cleaner. Okay, and so like this is always the big challenge of the subject, and I can tell it to you as somebody who used to do a lot of mathematical research. It's like there are so many times where you're trying to do a math problem and you know the answer, like you know what's supposed to happen. It's just a matter of can you write down in some way something that makes clear what is supposed to happen. Sometimes it's actually really hard. And usually what's actually true, interestingly, is like the clearer your intuition is on it, the harder it is to make clear mathematically.
That's
which is frustrating.
It's just the way it is. It makes sense. Yeah.
So does anybody want to supplement at all what Ankur did with their work, with their response to this question? Part of what makes this question tricky is we recognize that the intermediate value theorem is definitely what's at work. Okay, we realize that because we're kind of saying the function needs to cross certain value in the middle, right? And that's just screaming intermediate value theorem. Okay, that's clearly what we should be doing. But the thing about the intermediate value theorem is the intermediate value theorem is the theorem that applies to one function. But here we have two. Here we have two functions. So an important idea that we can take away from the solution to this problem is many times where you have a theorem that relates to one object, but then you want to apply it to two objects, you need to find some way to combine those two objects into one object. So here's the suggestion that I'm going to make. Let's let h of x equal f of x minus 2x. That's going to be the suggestion. All right, and then my question to you is, what can we say about h of a and h of b? Anybody tell me, Jacob?
So the h of a is positive to each of these things?
Yeah, I have to remind myself what is the setup. They have opposite signs. That is definitely.
Oh, yeah.
I forget which is which. I forget which one I said is greater first. Can somebody remind me? Which one is greater at f?
G of x is greater first.
Okay, so then if g is greater first, then this value is going to be negative, and this value is going to be positive. And so, two-part question. First part, does the intermediate value theorem apply to the function x? Does it satisfy the hypothesis of the intermediate value theorem? What is the hypothesis of the intermediate value theorem? Good, yeah, we need a continuous function. That is the hypothesis. So the question is the function h continuous? How would we argue that it is continuous?
The sum of two continuous function is continuous.
The sum or difference of continuous functions is continuous. The difference of continuous functions, so it is continuous. Okay, so the intermediate value theorem applies. And so what conclusion can I now make using the intermediate value? For the function h.
So there must be a point where h of x equals to 0, so that fx equals to g of x.
Good. Somewhere between A and B. So here's our picture for f and g. Now what we've done is we've kind of smushed it into this other picture. I have this function h. The function h is negative at x equals a. It's positive at x equals b. And it's continuous. Okay, so it can't hop. Since it's continuous, it can't hop over y equals 0. You gotta hit it. And where it hits it, the value of the function h is 0. Okay? Well, if the value of the function h is 0, what does that tell me? According to the definition, as Sarah just said, it tells me that f of c minus g of c is 0, which in turn implies that f of c is equal to g of c. So there is a solution. And that's a very convincing, clean argument. Very convincing and clean argument. But the extra jump that I had to make was I had to combine the two functions into one. That's a really common idea in proofs of this type, so I hope that you'll remember this idea. This is a very important idea. Any questions? Let's thank my man Andre. He got volunteers. Stepped up, did a nice job. Okay, now we're going to look at Sarah's solution. And now I have to go to my Google Drive. This is from Sarah. Okay. Okay. We'll zoom in. There's number 1. Number 2 is here. Okay. Sarah, go for it.
Okay, so I basically took away the idea that we used in exercise 1, and because we know the range of the function f, and both the range and the domain of function f is 0 to 1. So we know f of 0 must not be smaller than 0, and f of 1 must not be greater than 1. And then, so I just created a function, let's call it g of x, with domain 0 to 1 and range to all the rational numbers, and define it as g of x equals to f of x minus x, because we're trying to find the unfixed point, which is x. And then, so since both f of x and I just created another function, h of x equals to x, are continuous, g of x is also continuous. And from f of 0 is greater or equal to 0, and f of 1 is greater,
Yeah, it
is
should be
smaller. Yes, that's smaller or equal to 1. We know that g of 0 is greater or equal to 0, and g of 1 is smaller or equal to 0.
Yeah, let's just make sure that we're all caught up with that. Okay. If I look at this equation here, if I plug in 0 for x, I get f of 0 minus 0, but f of 0 is not negative. It's between 0 and 1. So g of 0 is definitely not negative. And if I plug in 1 for x, I get f of 1 minus 1, but f of x is at most 1. So f of 1 minus 1 is non-positive. Okay, so g of 1 is non-positive. So this is what she says here. G of 0 is non-negative, and g of 1 is non-positive.
And from intermediate value theorem, we know there exists a point between 0 and 1 where g of x equals to 0, so that f of x equals to x.
Yeah,
and
very
that's,
good.
yeah.
That's very good. That's a fixed point. Does that make sense to everybody? It's the same picture, really. Let me kind of go to the board again and draw this picture. Here's 0, 0. Here's 1, 1. Here's the line y equals x. Okay? And then I have some function, and the function f, it has as its domain the same interval from 0 to 1 and range from 0 to 1. So I don't know where it starts, and I don't know where it finishes. Maybe it finishes here, or maybe it finishes up here. Okay, it could finish at y equals 1, I don't know. But at some point, it's going to have to hit this line. No matter where I start, it may be all the way over at the right endpoint, but I can't draw a line so that it has I can't draw a graph, I shouldn't say line. I can't draw a graph that has a domain of 0, 1 and a range of 0, 1 that misses this line. It has to hit it somewhere. This is what Sarah has seen. And the reason is basically the same. It's the original, it's the same as this picture. The value of the function f is higher at first and lower at the end, so it has to be equal somewhere in the middle. Now, it could be equal at the start or equal at the end, but if it's equal at the start or equal at the end, then you're done with the problem, right? If it's equal at the start, then f of x equals x. If it's equal at the end, if it's equal at the start, then f of 0 equals 0. If it's equal at the end, then f of 1 equals 1. So the picture is the same. All right. Any questions? Sarah, great job. Thank you. It's actually a very important idea, the idea of fixed points. This is kind of the most basic fixed point theorem. So when you talk about a fixed point is just a point for some function where the output of the function equals the input of the function. You put something into the function and you got out the same thing. So nothing happened, right? The function didn't do anything. That's why it's called a fixed point. The function fixed the input. It didn't do anything to it. Fixed points have a lot of applications in different areas, and two of them that I could list for you immediately are differential equations. Okay, so like if you have a fixed point, that's kind of an equilibrium of some system, right? You put in some input to some system and you get out the same thing, that means that the system didn't change. So if you're in some position where a system is not changing, that's an equilibrium to the system. And then that's like the big idea of fixed points. And then that idea of equilibrium also has applications to game theory, right? Some of you I know we have talked about game theory at USN a little bit. I don't know if you guys, if the other schools have or have not, but this was the big idea of Nash. How many people saw the movie A Beautiful Mind? Oh, great movie, Best Picture, 2001, I want to say.
I liked it.
Best Picture, and yeah, it has math stuff in the movie, so win-win. Great movie, math in the movie, and his big idea was this idea of thinking about like finding the best strategy for a game in terms of functions and fixed points, which basically was like you take some strategy and you put it into some function that tries to find a better strategy. And then if the function outputs a better strategy, you put that strategy back into the function to try to find an even better one. And then when the strategy, if you reach a point where you put a strategy into the function and the function gives out the same strategy, then that strategy is like the best one possible. But that's also a fixed point, right? Because the strategy that I put in is the same as the one that I got out. Input and output are the same. So fixed points are very useful in game theory. They're in the study of game theory. A fixed point is kind of an optimum strategy according to this notion of Nash. Nash had this idea of thinking of using functions in this way. Okay, so yeah, and there's like a whole very broad theory of fixed points and trying to find fixed points. There's a lot of cool theorems in that area, but they're more advanced than we can handle at this time. But this fixed point theorem that Sarah just proved is kind of a nice, very basic. So that's very good. Okay, nice work. Then we're going to Hannah Aaron for the last one. And there it is. Okay, we're going to plug back in. So now we get into Euler characteristic, which this is going to be the subject of our study for the next day and a half. Just a reminder for all of us, Hannah Aaron, what is Euler characteristic of a polyhedron?
It is the number of vertices minus the number of edges plus the number of faces of the...
Good. Vertices minus edges plus faces. And what did we say in the video about, or did we do, I'm trying to remind myself, in the video did I compute it for a cube? Okay, well we'll do that.
No, I think you did.
I did?
You did? Oh. Oops.
Yeah, it was like the last. It was the last Olympic exercise.
Oh.
Okay.
Okay. So in this exercise, we're looking at a tetrahedron, and I said that a tetrahedron has 4 vertices, 6 edges, and 4 faces.
Yeah, just say a little more about that. Where are these things?
Okay, I guess. Not draw.
Yeah, go ahead to the board. Yeah, and erase everything or anything, wherever you want to erase.
So, I'm not very good at drawing, but it kind of looks like this.
I think you have too many sides. Or am I? No, you're okay. Sorry.
Okay. No, I do.
Yeah, you should have
Okay.
3 and then.
Yeah. Okay, that looks good. That looks good.
Okay.
Okay.
So the 4 vertices are here.
1 at the apex and then 3 on the base. Good.
And then you have the 6 edges. 1, 2, 3, 4, 5, 6.
Yeah. I always like to say you have 3 edges on the base and 3 edges that connect the base to the vertex or to the apex.
And then the 4 faces are 1, 2, 3 in the base, and then 4 is like what we're looking at right now.
Good.
Good. So.
So just go ahead and write down, if you would, what is the computation for the...
Okay, so take vertices minus edges plus faces. So that's 4 minus 6.
2. Good. Very good. Any questions there? All right. Aaron, good work. Thank you. Okay. Yeah, so one thing that we noticed, so we started to talk about in the video, what is topology? What are the questions that we think about in topology? And basically, there's 2 kind of key notions in topology. One is the notion of continuity, and then we also have kind of like the geometry side of it. So what we saw in the video is if I take a cube, then I can compute its Euler characteristics. Okay. How many vertices are there? 4 in the front, 4 in the back, that's 8. How many edges are there? 4 on the top, 4 on the bottom, 4 that connect the top to the bottom, that's 12. How many faces are there? 4 around the outside, 1 on the top, 1 on the bottom, total of 6. So the Euler characteristic here is 2.
What?
Euler characteristic is 2, which is the same as the Euler characteristic for the regular distribution. So we call the Euler characteristic, what was the term that I gave to this sort of thing? Something that doesn't change, or I hope I defined this.
Invariant.
It's an invariant, topological invariant. Okay, very good. In other words, if I take some shape and I change it continuously, so that adverb continuously is really essential. I take this shape and I change it continuously. Continuously means, we know this in the context of functions, right? Like, what does it mean for a function to be continuous? It means that it's uninterrupted. There's no holes in it, there's no breaks or anything like that. This function would be discontinuous. Have this break right here. So, if I want to change a shape continuously, I can't break it. I can't tear it, I can't cut it, I can't do anything like that, okay? The only thing that I can do is I can treat it like it is made of some pliable material and I can smush it around or stretch it or anything like that. These are continuous changes in figure. So you could probably imagine that, like, if you had a bunch of Play-Doh and you had a cube of Play-Doh, that you could smush the Play-Doh around and get a regular tetrahedron of Play-Doh. Okay, you probably could imagine that. And so the Euler characteristic does not change if I smush the Play-Doh or anything.
So it doesn't have to be regular.
No, it doesn't have to be regular.
Okay.
Yeah. And as you could also imagine, like, just imagine that instead of a cube, you had this super long rectangular prism, right? That would not change the number of vertices, edges, or faces. That would be a continuous change. And now, just to kind of, so does everybody follow this sort of computation? Yeah, and so, like, you could imagine some other Platonic solid. Those of you who know about Platonic solids, you could imagine, icosahedron or whatever your favorite Platonic solid is, and compute its Euler characteristic, and you will get 2. I don't want to go through all of those. But what I do want to do is this. Okay, we're going to find a solid that has a different Euler characteristic than 2. So here's what I want you to do, and what we're going to realize is we're going to have to think about it a little bit more carefully, okay, because what we're going to see is one of the quantities is going to be a little bit trickier to define. What we're going to do, and I'm going to try to draw this pretty big so that we can get a nice picture. We're going to take a cube and we're going to drill a hole through the center of it. Okay, so it's going to look like this. Yeah, I just want to make sure we can all see it. And then I'm going to cut out a solid from the middle and drill all the way through.
Does it matter that it's small on the bottom, small on the bottom?
No, I didn't need to do that. I'm just bad.
Okay.
So you would imagine I have this cube and I drilled out this rectangular solid from the middle. And then now what we want to do is we want to compute vertices minus edges plus faces. Okay? But then the key question is this. This thing that I have on the top of what used to be a cube is now kind of debatable if I should call it a face. This it's kind of part of the face. Is it a face or is it not a face? So that's kind of a tricky question. Okay. And so what we do to resolve the question is this, and this is an idea of Euler. Okay, so Euler, and of course it's called the Euler characters. So a lot of these ideas are due to him. I don't want to go into too much detail about this because it can get pretty technical pretty quickly. But what you can do is, on these different faces, you can draw graphs. Okay, you can draw additional segments. So that's what I'm going to do. I'm going to draw some additional segments. What I'm going to do is, I'm going to take the inner vertices of this little square, and I'm going to connect them to the corresponding outer vertices. And so what this is doing now, this is adding edges to the figure. Yeah, I'm adding edges to the figure. I'm not adding vertices, but I am adding faces. I am adding faces. Because now, this object here, this little trapezoid that I have with red on these sides and then black on the top and bottom, this trapezoid is a face, okay, because there's no hole in it, right? That's topologically equivalent to just this square, right? I could smush this face around and just get a square. So we made the agreement that we define a face to be something that is topologically equivalent to a square. Then I do the same on the bottom. Jake.
I just don't get how you're adding, that's adding edges. Are you just drawing lines?
Well, okay, yeah, but now this line is now an edge because it connects two vertices.
Is this line like pointed upward, sort of?
No, it points from the outside of the cube to the inside.
Okay.
Both endpoints of this edge are on the top of the cube.
So you just have an edge just defined as connecting two vertices.
Yes, very good. An edge by definition is a line that connects two vertices. Yeah, it doesn't add anything geometrically to the figure. The figure still looks the same, but I just draw it with these extra edges in it so that I can identify its faces better. Because the question of is this top thing a face or not is questionable.
What if you knock out one of the edges up and then? Why isn't that also considered?
Good. Yeah, true. Like what I could actually do is I could just delete these two edges.
Yeah.
Let's not do that for now. Okay, we can do that. And so actually that would be a good exercise because we'll see how adding and subtracting edges doesn't change the order of the characters. That'll be nice. Let's everybody take a couple of minutes, and now with this object that we have here, let's compute the Euler characters. Okay, so let's everybody take a couple of minutes to do that. And we'll talk about it together.
Alright, I forget this is the inner square, does that count? Those are edges to stick.
Anything that connects two vertices is by definition an edge. Good. That's where it is.
Do we count the faces on the inside of the rectangular solid?
Yeah, we do.
Okay.
All right, people seem to be basically done. Serena, what'd you get?
12.
12? How'd you get it?
16 vertices, 20 edges, and 16 faces.
All right, let's count them up. So we got vertices, 4 around the outside of the top, 4 on the inside of the top. So 8 vertices on top, 8 vertices on bottom. That's a total of 16. So I agree with that. Count your edges for me.
Do the 4 edges on the little square count?
They do, yeah.
Did you take that together? Yeah.
Yeah, if we look at the top, we have 4 edges around the outside, 4 edges around the inside, and 4 connecting the inside to the outside. So it's 12 on top,
So 20.
12 on bottom, and then we have 4
So it's
around
8,
the outside and 4 around
The
the
Euler
inside.
characteristic becomes 8.
No,
4 times 8.
you're still missing.
So 32.
It's 32
Yeah,
total
it's
edges.
32.
Yeah. 12 on top, 12 on bottom.
So 0.
Yeah.
It'll be 0 at the end. 12 on top, 12 on bottom, 4 that connect the outside of the top to the outside of the bottom, and 4 that connect the inside of the top to the inside of the bottom. So 12 plus 12 plus 4 plus 4 is 32. And the number of faces, Serena, you got 16.
Yes.
Yeah. Go ahead, tell us about it.
Tell us about the number of faces.
Yeah, where are they? Where are the 16?
Oh, okay. Well, it includes like the largest faces on the 4.
Okay, good. Go around the outside.
And then the 4 like trapezoidal faces on top and bottom.
Good. That's
And then
12.
the 4 faces on the inside.
Good. Nice. That's 16. Now your vertices minus edges plus bases. What are characteristics of 2? Yeah, so actually what you would see is if you treat the things that are on top and bottom as if that's just not a face, it's not anything, then you would get the right result. Okay, you would have 8 vertices on top, 8 vertices on bottom for 16. You would have 8 edges on top, 8 edges on bottom, and then 8 edges connecting top to bottom, so that's 24. And how many faces do you have? You have 4. So hopefully that worked out. Or no, you have 4 around the outside, 4 around the inside. Yeah, so you have, how did that up? You need 16 vertices. How many edges was it? 32, and then, I have to write, sorry. So, edges, vertices, we have 8 on top, 8 on bottom, that's 16. Edges, we have 8 on top, 8 on bottom, and 8 connecting the top to the bottom.
You'd have 12 on top and bottom.
Yeah.
Pardon me?
You'd have 12 on top and bottom.
No, we're talking about like in the original set. Like if I don't.
Oh, okay.
You're right. This is the original set, or this is the setup that I've drawn.
Oh, okay,
here.
okay, I got you.
I have 16 vertices. I have 4, 4, 4, 4, 4, 4. That's 24, right? Edges. 8 on top, 8 on bottom, 8 connecting the top to bottom. That's 24. And then, 8 faces. 4 around the outside, 4 around the inside. So it does add up. It does add up to 0 if you treat the thing on top and the thing on bottom as if it's not a face. But it's not immediately clear you should do that. In particular, people's intuition generally is to do the opposite. They want to say anything that has any measure of area should be a face, but you actually shouldn't do Okay. So adding this hole through the middle decreases the Euler characteristic by 2. What's up, Jacob? What does it mean? Well, what we're going to see is it's actually an interesting result. Okay, it's an interesting result. And also, like, yeah, so now is where we're going to kind of make the connection to the soccer ball question. Topologically, this cube is equivalent to a sphere, okay? Because I could take this cube and I could smush it into a sphere, right? If anybody's ever played with Play-Doh, which hopefully you all have, because it's fun, you could smush that cube into a sphere. So these things are topologically equivalent. So I'll use this symbol. Yes. And so we say that the sphere has Euler characteristic 2. Now, what does it mean for us to say that the sphere has Euler characteristic 2? That might seem a little weird because the sphere does not have really vertices or edges, okay? But the right way to understand it is to think about if I drew a graph on the surface of the sphere. And by graph, I don't mean like your y equals f of x graph. I mean like a collection of vertices and edges and faces. So like if I put some points on the graph, or points on the sphere, and then I connect them, then the number of vertices here would be 3. I've made 3 vertices. They're connected by 3 edges, and there are 2 faces. One is the interior of this little triangle, and the other is the exterior, the rest of the sphere. Whoa. So that's the right way to understand Euler characteristic for a sphere, something that doesn't in and of itself have vertices and edges. And so that idea is the idea that we're going to take advantage of when we come to the soccer ball question, because what is a soccer ball other than a graph drawn on a sphere? Right? You have all these vertices, and you connect them, and then it makes hexagons and pentagons, and then we're going to address the question of edges and faces and vertices. So that's what you're going to look at for class Friday. Topologically, what is this equivalent to?
Circle with a hole drilled through.
Yeah, sphere with a hole drilled through it. What is that shape topologically called? Does anybody know? What was it, Lana? You were a torus. Yes.
Yeah.
You seemed like you were unsure what to do with that last consonant.
Torus? I thought you were saying torus.
Now, here's one of the core things that you can learn, and you will learn from me, possibly the worst artist who ever lived. You can draw a very nice torus in the following way. I'll show you. This is one of the great things you can learn from this class. Draw a circle to the best of your abilities, okay? Doesn't have to be a perfect circle.
Oh my god.
Or actually, an oval is a little better. Yeah, I don't appreciate the laughter. Yeah, and then what you do is this, okay? You make a little U inside, and then you make an upside down U, but not all the way across. You kind of start in the interior and go like that. And now it looks like a torus.
Wait, how?
Wait, I don't see it.
All of you are terrible. All of you are terrible. That is a great torus.
Wait, what are we looking at?
It's a donut.
Oh my god,
That's
it's
actually really good.
I didn't realize that's what it was. Until
What do you mean?
If you made a donut that had like square sides, this is what it might look like. This would be a donut with square sides. But then a regular donut, like if you actually molded the dough so that it looked like a donut, it would look like.
No, that's good. I'm sorry about laughing.
I thought isn't that.
All right, class is over.
Now that
I'll
was
see you all on Friday.
donut.
See you all on Friday. More Russian hack games tomorrow. And
You guys missed it. None of us died.
there will be
We might have died, but we
soccer
didn't.
ball Friday. See you then.
What day did we miss that? Was Russian?
Yesterday.
Okay, do this